Okay, so then this video I'd like to go through an example of our three constraint handling methods, the transformation, Lagrange, and Penalty methods for a relatively simple structural model. Okay, so the model is this beam shown down here. Okay, so the elastic properties for the beam are given here. E, A, and I are shown there. There's a transverse point load applied at midspan. There's an axial or horizontal load applied at the end. There's a uniform distributed load across half the span, and there's also a support displacement right here at the roller support. Okay, so the degrees of freedom for the model is that there's 5 unconstrained degrees of freedom and 4 constrained degrees of freedom. Okay, so with no constraints, all right, i.e. all the members are flexible in their axial and flexural response, it's pretty straightforward to show that the stiffness matrix is this 5 by 5 shown here. Okay, and the total nodal load vector, PF tilde, which includes the nodal loads, the rigid body load effects from the member loads, as well as fixed and basic forces and the effect of support settlements, is this vector right here. Okay, so the resulting nodal displacements of the unconstrained structure, i.e. from solving KFF UF equals PF tilde, okay, is shown right here. Okay, and then the reactions that we recover from this system are shown here. Okay, so that would be reactions that look something about like this. All right, so that's 10. This is 21.968. This is 1912.3. This is kip inches, right? And then 0.032118 there. Okay, so the support settlement does some pretty funky stuff here, but you know, the applied loads, 10 kips there, 10 kips there, distributed load here of what was it, 0.1 kips per inch, I believe. Okay, so you can verify that all that satisfies equilibrium. Okay, so that's with the with no constraints. Okay. Okay, so now if we assume that the entire beam is axially rigid, and then only the right span is also flexurally rigid, i.e. we have something like this, where the whole thing is axially rigid, okay, and then the right span over here is also flexurally rigid. Okay, so this is 120 inches long, and that's 120 inches long. Okay, so this gives us 1, and then 2, 3, 4 constraint equations. All right, 1 over here for the axial rigidity, and then 2 for the axial rigidity of this element, and then 3 and 4 for the flexural rigidity. Okay, but in doing so, with those constraints, we can show that the system of constraint equations is given here, right, where this is constraint matrix CF, and then this is the right-hand side vector R, which is owing to the support settlement at the right support. Okay, so after loading this into Python, all right, and then using RF and some other operations, all right, we can show that what results is there's only one retained degree of freedom, right? There's 5 unconstrained degrees of freedom, and then there's 4 constraints. Okay, so that leaves only one retained degree of freedom, which is UF5, which is the rotation at the roller support. Okay, so then this becomes CFR, all right, and then the remaining 4 columns of CF go into CFC. Okay, And then with those partitions of the constraint matrix, we can use more algebraic operations in Python and get the following transformation matrix, okay, which is 5 by 1. Okay, so there's 5 unconstrained degrees of freedom, and then there's 1 retained degree of freedom. So that's why it's 5 by 1. Okay, so this is 0, 1, negative 20, okay, or excuse me, 0, negative 120, 1, 0, 1, okay. So that indicates that we have this as our display shape when we have our unit value of our one and only retained displacement. Okay, so this gives us down here, this rotation is 1. Okay, this deflection right here using small angles is just 120. Okay, and the horizontal motion of this joint is 0, and the horizontal motion of that joint is also 0. Okay, so that's where we get the 0, negative 120, 1, 0, 1 in our transformation matrix. Okay, so that's all the nodal displacements at the unconstrained degrees of freedom due to a unit value of our retained displacement. Okay. Likewise, our vector of nodal displacements due to support displacement, this UF0, okay, is 0, negative 0.5, 0, 0, 0. So that tells us what happens to the structure when we impose our support settlement of 1/2 inch to the constrained structure. So this entire piece right here moves down as a rigid body. It does not rotate, okay? And in doing so, it pulls this node down 1/2 inch, okay? There's no rotation or horizontal motion at this middle node, okay? And there's no horizontal motion at this node, okay? So that's where we get this 1, 2, 3, 4, 5 unconstrained degrees of freedom, and in the presence of the constraints, this support settlement pulls degree of freedom 2 down 1/2 inch. Okay, so what happens with the transformation method? Well, we can show that the transformed stiffness matrix is just going to be a scalar value, okay, given there. And then the transformed load vector on the right-hand side is also going to be a scalar value. And then solving this one equation, we get our one and only retained displacement, which is shown there. And then we can recover all of our nodal displacements through our transformation equation. Okay, so we get the 5 displacements. Okay, and you can see here that the 2 horizontal degrees of freedom, 1 and 4, are both 0, which should make sense because recall the beam looks something like this. All right, and if the whole thing is axially rigid, then this joint's not going to move left or right, and this joint's not going to move left or right either. All right, so that's why we have those 2 zeros, okay? And then also you see the degrees of freedom 3 and 5 have the same value, okay? Which just indicates that, this flexurally rigid portion over here just moves as a rigid body, or rotates as a rigid body, has the same rotation on both sides, okay? All right. So if we use these displacements to recover the reactions, using an operation like this, all right, then we get these reactions shown here, right, which are 0, 22.137, 1952.9, and 0. Okay, so let me just draw those on here with the applied loads. 10 kips, 10 kips, 0.1 kips per inch. Okay, so that gives us a reaction of 0 there, 22.137 kips there, 1952.9 kip inches there, and then 0 here. Okay, so I think it's pretty easy to tell that these reactions do not satisfy equilibrium, certainly not horizontal equilibrium. We have 0 at the fixed support, 10 kips there. These two vertical reactions do not add up to 22 as they should. Okay, so the transformation method as implemented at the structural level here doesn't give us the correct reactions. Okay. Okay, how about Lagrange multipliers? Okay, so in this approach we use CF and R from the constraint equations to form a larger system of equations. Okay, so we get this and this. All right, so this part, the lower right block down here is all zeros. This is CF. This over here is CF transpose. Okay, and then this is our original KFF. Okay, and then on the right hand side we have our total nodal load vector PF tilde, and then the R vector down there. Okay, so solving this system we get our nodal displacements up here, and then down here we get our Lagrange multipliers. Okay, all right, so again you can see that the nodal displacements satisfy the constraints, right? The degrees of freedom 1 and 4 are both 0 displacement, all right? So there's no horizontal displacement due to axial rigidity, and then the rotations 3 and 5 are both the same. All right, so these are the same numerical values we got with the transformation method. Okay. All right. Then the Lagrange multipliers we can map out to the elements that had constraints. Okay, so this first Lagrange multiplier was due to axial rigidity of element 1. Okay, so we have an extra Lagrange multiplier force of 10 kips for element 1. And then the next three Lagrange multipliers are due to the three constraints of element 2. 1 for axial, 2 for flexural. That's 10 kips there. And then 4.4048 kip inches there. And then basically 0 at the other end. Okay. All right. So if we add these Lagrange multiplier forces in to our force recovery, all right, as kind of indicated down here with this expression, actually this part should not be there, okay, then we recover reactions that satisfy equilibrium, okay. So we're picking up the forces that the transformation method left out, okay, by adding these forces into our force recovery for each element, okay. And then finally we have the penalty method, okay. So if we use the same penalty number alpha for all the constraints, then we can just scale these objects, CF transpose CF and CFR, as shown there. These are from our constraint equations, coefficient matrix, and the right-hand side vector. Okay. So look at what happens with a small penalty value. Let's say alpha equals 10. Okay. In this case, if we multiply this matrix, all the entries by 10, and then add it to KFF, we get this penalized stiffness matrix, and then the associated total nodal load vector on the right-hand side, which is the original PF tilde, plus this vector over here multiplied by 10 and added into PF tilde. We get this right-hand side vector, and then we can solve for the nodal displacements. All right, and you see that this one should be 0, but it's not. This one should be 0, but it's not. And these two should be equal, but they're not. Okay, and that's due to this low penalty number. Okay, And then the penalty forces associated with this value of alpha are shown here. Okay, and those are relatively small, so they're not enforcing the constraints. Okay, and then you can recover the reactions associated with the small penalty number, but I'll skip over that, and we'll go into more detail with that with this larger penalty number of 10 to the 8th power. Okay, so if we scale CF transpose CF by 10 to the 8th and then add it to KFF, all right, then we get this penalized stiffness matrix, and then with alpha being 10 to the 8th, we get this nodal load vector. Okay, and then solving, we get nodal displacements that come very close to the exact solution. All right, so 1 and 4 are getting very small. All right, 10 to the negative 8th, 10 to the negative 7th, and then 3 and 5 are getting to be very close to equal. Okay, and then the penalty forces associated with that system are given here. Okay, which we can kind of treat as Lagrange multipliers mapping onto each element. All right, so for element 1, there's one constraint, which is axial rigidity, and this is 9.9995 kips. And for element 2, we also have 9.9995 kips, and then 4.3399 kip inches. Okay, and then a small force 28975 kip inches, or small moment, I should say. Then adding these forces into our force recovery for the elements, we can get these reactions here, all right, which can be shown to satisfy equilibrium. Okay, so if we have, that's applied load 10 kips, 0.1 kips per inch, this is 10, and 21.963 kips, 0.036654, and then moment over here of 1911.2 kip inches. All right, all that equilibrium should check out. Okay, so as you get to higher and higher penalty numbers, we converge to the theoretical solution. Okay, but what's a large enough penalty number is the question. All right, and kind of the answer is your penalty number should be at least 2 to 3 orders of magnitude higher than the associated characteristic stiffness values of your constrained elements. So EA over L for axial rigidity, EI over L. So a penalty number that's say 1,000 times EA over L should do a good job of enforcing axial rigidity. Likewise, 1,000 times EI over L should do a good job of enforcing flexural rigidity. Okay, so what I've plotted here is the UF4 and UF5 displacements, okay, which are the axial displacement at the free end over here. So that's UF4, and then this rotation UF5 down here. All right, for increasing penalty numbers. Okay, this is log 10 on the scale, and then this orange line here is our numerical value of EA over L for this element. Okay, where L is equal to 120 inches, just for this one element here. Okay, not the whole 240 for the whole beam. All right, and then this orange line down here is EI over L, not EI over 2, but EI over L. Okay, for the same span, 120 inches EI. Okay, so as you have values that are less than EA over L, up here and less than EI over L down here, the constraint is not enforced very well. Okay, but as you get to 3 or 4 orders of magnitude higher than EA over L up here, you see that the constraint is satisfied. Zero displacement there. Okay. All right. And then likewise for the flexural constraint, the exact solution is given down here as you get to 2, 3, 4 orders of magnitude higher than the EI over L. This starts to be satisfied. Okay. But you notice that as you get to very high values of the penalty number, the numerical solution starts to break down due to round-off errors. Okay, so you can't make your penalty numbers astronomically stiff. All right, if they go too high, then it starts to clobber out all the realistic smaller values within your stiffness matrix. Okay, but if you just stick with 3 or 4 orders of magnitude higher than some characteristic stiffness of your system, it should do a good job. Okay, so with that, hopefully that kind of shows the differences between the constraint handling methods, and thank you for watching.